So welcome to this Quintus Tech Talk. Today we're going to be talking with Sebastian Proper from RISE, the Research Institute of Sweden. Sebastian's one of the foremost researchers in the area of aluminium alloys for additive manufacturing and working a lot with lightweighting of products. So welcome to this talk, Sebastian. Can you give us a bit of background about yourself, where you come from, what you do and what you're working with?
Thank you. So my name is Sebastian Proper. I have a master's degree in material science from Uppsala University. I've been working as a researcher at RISE in additive manufacturing for 4 years now. There I work along the entire value chain. So I work with design for AM, process optimization, process parameter development for new materials, also working hands-on with the machines, and then working with the post-processing and characterization. So the entire value chain, basically.
So Sebastian, can you tell us a bit about what you're researching at the moment, what the main focus areas are?
The main focus area at the moment is thin wall capabilities of aluminum printed parts. So we're comparing different kind of post-processing routes to see how it will affect the mechanical properties of the printed parts. We're talking about doing heat treatments, hipping, different surface finishing, so machining and heatization, and also comparing different process parameters to see how they will affect the performance of the printed parts.
So, I mean, as part of this, I guess post-processing with hot isostatic pressing and high-pressure heat treatment is a kind of a key area. What are the main areas where you can see something really helping there?
One main area is when we want to decrease the production time. We can use different kind of process parameters to increase the time of the printing, so increasing the speed of the laser or increasing the layer thickness of the powder bed. But that often leads to a poorer printed part, so much more porosity in the printed part. But if you can reduce the printing time with half, then we can do post-processing like HIP to close the pores and have an all-over faster production time than if we would have printed with a high-density part from the beginning.
Right, and I know that you have this fantastic graph showing the printing speed and how that can be affected by the printing parameters. What kind of speed increases have you been looking at?
So we've been looking at increasing the laser speed to up to 2,500 millimeters per second almost. We decided on a window where we were comfortable in managing to print the parts. We were also looking at different layer thickness, so using the kind of standard of 30 micrometer layer thickness and increasing it to 70 micrometer layer thickness. That could even be increased more to up to 90 micrometer layer thickness if we wanted to, but we wanted to stay in a comfort zone, so to say, to be able to print good enough parts. So we were able to print these parts with quite high density, but not good enough.
Okay, and then you were able to close that later on with the high pressure heat treatment then?
Yeah, so we took some of the most promising parameters that have high speed but good enough density, and moved on to try to close those with hipping. And we were able to close some of them. We could see that if you have too much open porosity in the printed parts, we could not close all of the pores sufficiently enough. But if we don't have too much open porosity, we could actually close a lot of the pores and get a good dense part.
Okay.
And print much faster.
And when you say much faster, how much faster can we achieve a fully dense part using this process with high-speed printing in combination with high-pressure heat treatment?
So we could eventually, what we could see was that we could print with almost 150% faster production rate using a faster laser speed and higher layer thickness.
Wow.
So that's a really good improvement, especially when we're talking about printing big parts that can take several days. We can decrease the production time a lot.
Okay, so if you can increase the speed so much, Sebastian, what's interesting then the quality of the parts after this high-speed process, including the high-speed printing and the hot isostatic pressing with heat treatment included. What's the quality like?
So when increasing the speed, we can see that we always get the maximum for the density, where we get the best density. But for the fastest laser speeds, we can see that we have a decrease in the density. So we are as low as 95-96% density, which is not what we want to have. So when introducing the hipping, we can close them and get a fully dense part. If the open porosity is low enough.
So Sebastian, can you tell us about what the results are based on the high-speed printing parameters in combination with high-pressure heat treatment, including the quenching technology we have, the URQ, Uniform Rapid Quenching, a kind of a mimic of the T6 heat treatment. What kind of mechanical results are you ending up with?
What we can see is compared to the as-printed state is that we get a slightly lower yield strength than in the as-printed state, but we see a vast improvement in the elongation before break. We get the kind of homogenization of the material.
Right. So what kind of elongation values are you looking at?
So when doing in as printed state, we have around 3%, but introducing the hipping, we can get up to 8-10% elongation before break, depending on the hip temperature and such, but in those kind of areas.
So I know that the goal of every engineer is to see their work being put into practice. And I'm holding a piece right here from a practical example of using your process now in connection with our high pressure heat treatment equipment. And can you tell us a bit about this and what it's all about and what kind of activities are ongoing?
Yeah, so the part you are holding is a suspension holder for the Formula student car at Chalmers. So the students there have designed the part using topology optimization and such to fit into the car and be as lightweight as possible. The part was then printed at our facility and then tested, and they could see that it broke in one of the areas, as you can see in the image. But then after introducing HIP, they could see that when doing the same testing condition, the part never broke. It was actually the glue fixating the mechanism when they were pulling the part that broke before the part, so they could increase the performance of the part a lot with introducing the HIP to the part. And it held during their competitions, so it never failed, so that's good.
Right, excellent. So it's actually been put on a car then?
Yeah, it's been driving in some different competitions, so it's a cool application.
And of course the car went faster than everybody else's car, I'm guessing.
I actually don't know about the results, but I don't think they won, but at least the suspension was not failing.
That's a really good a good topic then for us. Yeah, so really nice. So So what you're saying is that there were fatigue cracks in the printed and heat-treated material, but not in the Hipton high-pressure heat treatment with the T6 integrated heat treatment.
Exactly. They got an initiation of the breaking at the part you're holding there in your left hand. So some kind of poor material properties in that area made it fail. So the fatigue was improved with the hipping.
And it's actually very light. So did you manage to save? How much weight do you know? Do you know how much weight they managed to save in the part?
Don't know that number, unfortunately, but I could imagine it's quite a lot. Since the design volume is quite big if you look at the bounding box of the entire part. So I could imagine they saved a lot of material.
Right, and at the moment I know we're working in a project on other suspension parts as well. So I think there'll be quite a lot of interest coming out of this with the publications, etc. Okay, so Sebastian, in the Research Institute of Sweden down in Gothenburg area, I know you're working with a fantastic application center at the moment. I mean, what's going on there? What are you working with? What kind of technologies can you offer to the industry?
Yeah, so it's a work that's been in progress for a couple of years now to get this to land. So we just launched it. So it's basically a playground for the Swedish industry to come and learn about 3D printing. So we are expanding our machine park, getting more technologies in. We are expanding with the post-processing, getting, for example, a hip in our facility, and the industry are really eager to learn. So it's really fun, but it's going to be a lot of work. But it's nice that the industry wants to learn more about 3D printing.
Yeah. So what kind of companies are involved in this center?
There are several, Quintus of course, but also some of the bigger Swedish companies, Volvo Trucks or Volvo Group. There's Volvo Cars, Höganäs, Alfa Laval, Siemens, and more. So it's an impressive lineup, and it's really fun.
Thank you very much for taking the time to talk to us today, and I think it was really, really excellent discussion, and looking forward to future cooperation with you.
Yeah, thank you for having me. It's been a pleasure. And if there's any companies or universities that wants to do collaboration, we are open for it. We do a lot of work with European and global companies and universities, so just feel free to contact us and we can get working.
Absolutely, and thanks once again, Sebastian. Tune in for some more tech talks as well online. I think there's a lot to be learned here, and the excellent work that's been done at RISE around the aluminium silicon 10 mg aluminium alloys. Excellent work. We got some really great results, and I'm sure this is going to make a huge difference to the industry going forward. So thanks once more for your time, and tune in next time.